All right, welcome to the lecture covering 3.2 material, domain and range. So we're diving a little bit deeper into this world of functions that we started with 3.1 in looking at input and output values a little closer. Okay, so we first run across just the idea of identifying domain and range from various types of graphs and information. So in creating various functions using data, we can identify different independent and dependent variables. Remember, domain is your input or your independent variables, which usually corresponds to an X value, and your range is your output or dependent variables. And we can analyze the data and the functions to determine what their domain and ranges are. In this section, we're going to be looking at different methods for determining these things. So if we take a look at this given data here for top 5 grossing horror movies for the years between 2000 and 2013, as well as market share of horror movies by year, we can begin to pull out, okay, what is the domain and what is the range for these values. So your domain for the top 5 grossing horror movies would actually be the set of points that comprises the year. So since, if you see with the blue bar graph there, we kind of skip around. We've got a 2001, a 2002, a 2007, 2004, and 2013. These are set dates that don't necessarily complete a full interval of date ranges. So if I were going to give the domain for this particular set of data, I would have to give it as a set. So here's the set, and I've got the year 2007, I've got the year 2001, 2002, sorry about the poor handwriting, 2004, and 2013. So that's just a set of separate points that we're thinking about. And then the range is going to be the same type of thing. Let's see, I have the range for the year 2007. My output is about 295, it looks like. And that's in millions of dollars. Hannibal in 2001 looks like it's at about 225. The Ring looks like about 175. The Grudge, maybe 140. And then The Conjuring looks about the same, 140. So separate, distinct points. Now, if we look at the market share of horror movies by year, notice we have no gaps between 2000 and 2013. So I can actually write this as an interval instead of as a set with separate dates. This particular domain starts at and includes the year 2000 and goes up through and includes the year 2013. And we'll learn more about how to write this later in this particular lesson. And it looks like our percentages would be separate values, just like the range for the first example here. I'm not going to take the time to write all these down, but you would figure out what they are and put them in your set notation there. Okay, so what do we have to be careful of when we are trying to identify domain and range when it comes to looking at equations and things like that? We have to be careful, and we'll revisit this idea later in the lesson. We have to be careful about square root of negative numbers, because this is going to produce an imaginary number. And we're not worried about the imaginary values. We want to know the real values that occur in the domain and range. We also have to be careful about division by 0. This will cause the entire function to be undefined, or a combination of both of those things. So we could have a square root of a negative number happening in a denominator, and we have to kind of combine how we think about that. Okay, so this is just a visualization of domain and range. You could think about domain as being sort of your potential energy, your holding area that contains the raw materials that are going to go through your function machine, and what comes out on the other side is that actual manifestation. So you've got domain you could think of as your potential, whereas range is your manifestation, and it moves through the function machine. So the domain gets put into the function, and what comes out on the other side is the range. We write domain and range as what is possible, excluding the values that are not. And our most preferred method for writing domain and range is interval notation, when possible. Okay, so a word about interval notation, which you should already be familiar with, so I'm not going to dive too deeply and spend a lot of time here, but I have it here for reference for you to jog your memory. So with interval notation, so we're talking about an unbroken interval from one value to another in either your domain or your range. And so whenever you're writing that interval, the smallest number from the interval is written first. And I'll go ahead and say that's going to be on the left, because we read it from left to right. Or from down to up if you're talking about range. The largest number in the interval is written second, following a comma. So you have a comma splitting your first marker of your interval, your least number. So maybe I should put your least value, or your, actually let me get correct grammar here, your lesser value for the first number that you write to the left, which is your lesser value. And then the rightmost number, so your last or your rightmost number, is your greater value. And they're separated by a comma. Parentheses are used to signify an endpoint value that is not included. We call that exclusive. It's excluded. And we can use brackets to indicate an endpoint value that is included, also called inclusive. Infinity, which we write or we symbolize with a sideways looking 8, and negative infinity, it's just the infinity symbol with a negative sign in front, are never included. In other words, you're always going to use parentheses instead of brackets, parentheses, with positive and negative infinity. So if I have a number line, running all the way out to the left is negative infinity, and all the way out to the right is positive infinity. Here's the origin at 0 there. Okay, so we'll take a quick glance at some of these examples here. So let's take a look at this one right here. So we have some value A is less than or equal to the X, the values that we want to talk about, which is also less than some value B. I would write that in interval notation as, and I'm going to write it bigger here in the box. Let me actually white out where it's already printed for you so that you can see this really well. I got to stick this to the board here. Okay. So to write that in interval notation, my leftmost or my lessor number is included because it says less than or equal to. So I'd write a bracket. I have my lesser number, and then I have my greater number, and I'm strictly less than that number, so I'm not going to include it. So this corresponds to open circle and closed circle in the old way you probably learned of graphing on the number line. And you can see on the graph or on the number line, this is going to correspond to some interval that starts at and includes A and ends at but does not include B. So Cyprian, if that makes sense to you and that's enough to jog your memory on interval notation, give me a green check from the drop-down menu, please. It's above your name with a checkbox. That's a drop-down menu, and you can either give me a green check or a red X. I see you're typing. Yeah, I'm well aware of that, Cyprian, and we've got graphs to look at later on, but this is prerequisite material, just knowing the notation of it. So we'll be doing examples later. I just need to make sure that you understand the difference between a bracket, a parenthesis, and how to use the infinity symbol. Okay. So we are asked here to find the domain of this particular function that is given as a set of points. If you've watched through the lecture 3.1, you will remember that functions can be given as a set of points, they can be given as XY tables, they can be given as an actual equation function, or they can be given as a graph. So this one happens to be given as a set of points, and when we're talking about domain, we're talking about all input values. So the domain of this function, it is discrete, it's separate points. We don't have an interval that's being filled by all of our input values like we would with a continuous graph. So this is literally a set, so I use the braces, and my domain is -5. It's just all of my X values, 0, 5, 10, and 15. So that's the domain for that particular set that is the function. And now if we move forward, moving into, okay, well, what if all we're given is an equation of the function? So the first thing that we want to do is identify any potential input values for that function. And we can identify any restrictions that may be input, but that may be on the input. We don't want to include those in our domain. And then we write the domain in interval notation if possible. So we were not able to write interval notation for this top example here. This is set notation, because it's just a set of points. It doesn't continuously stream from -5 up to 15. It's simply these separate values, -5, 0, 5, 10, and 15. To be able to write an interval, it has to be continuous. So we have this first example to look at, and it's a quadratic, so it graphs as a parabola, which is what you were just asking about a moment ago, x squared minus 1. Now I'm going to take you out to my desktop and share my desktop with you, and we're going to look at a graphing calculator here. This is just www.desmos.com. It's a free graphing calculator. So x squared minus 1. All right. So let's take a look here. Now, let me actually take a screenshot of this, and we'll bring it back to our whiteboard so that I can draw on it. Okay, so if we just want to think about the equation, not even looking at the graph, and we're trying to figure out domain and range, what we would have to ask ourselves for this particular function is, are there any real numbers that I cannot square and then subtract 1 from? So that's my question to you, Cyprian. Are there any real numbers that you can think of that are off limits for squaring? In other words, is there any real number that I cannot multiply by itself and then subtract 1 from? And I see you're typing. -33. Okay, so just to show you, -33 squared minus 1, I have to grab my calculator on that one, Cyprian. F of -33 would be -33 squared minus 1. Okay, let me grab my calculator real quick. I'll be right back. Okay, so -33 squared actually comes out to a real number, 1089, and then I subtract 1, and that leaves me with 1088. 1088 is a real number. So there's no problem with squaring -33. What made you choose -33, Cyprian? I'm curious. Like, why would -33 pop into your head as not being able to be squared and have 1 subtracted and end up as a real number? And I see you're typing. For those of you watching the video, Cyprian's still typing, so I'm just waiting to see what he has to say before we move on. And Cyprian, for the sake of the video, for future questions, it may be best just to use your microphone if you have the ability to, just so that we don't have all this lag time in the middle of the video. Okay, so while Cyprian is finishing typing, I will come back to his statement about -33 here. But just so you know, does odd and even numbers matter? No, absolutely not. All odd and even numbers are real numbers. So we're just trying to identify if there are any real numbers that we can't plug in here and square and then subtract one from. And in this case, since this is a quadratic function because it is squared, any quadratic function has no restrictions on the domain. In other words, I can choose anything my little heart desires as long as it's a real number to plug in, and I will receive a real number output from that. So the domain for any quadratic function, it goes all the way from -infinity to +infinity. Notice I use parentheses with both of those because you never include infinity, and I represented my lesser number on the left separated by a comma with my greater number on the right. So there are no restrictions in this. Basically, what this says is all real numbers are part of the domain. And we'll take a closer look at the actual graphs here in a moment. I've got some graphs that explain looking at it graphically here. So there are no restrictions. You can see you chose -33, which is a real number, and it came out to 1088, which is also a real number. So there's no problem with that. The only thing that we have problems with are when imaginary numbers come up, and we get those by taking even roots of negative numbers, and we have problems with having 0 in a denominator because that causes it to be undefined. All right, so if we look at this next example here, are domains on the x-axis only and ranges on the y-axis only correct? So domain and range were defined in lecture 3.1. Have you watched that lecture yet, Cyprian? Okay, yeah, that'll clear all that up for you. Okay, so here we have a cubic function because its degree is 3, right here. Degree is 3. And so I'll just give you a quick sketch of what a cubic function looks like. It comes up from negative infinity, kind of makes an S across, and then it goes off to positive infinity. All right, and just like the quadratic function, I will also say any cubic function also has no domain restrictions. So it's going to have the same exact domain as your quadratic function. So the domain is negative infinity to positive infinity. Now we can certainly take a look at a graph that does not have a domain of negative infinity to positive infinity. And we'll take a look at those in a little bit, but a good rule of thumb to remember is anytime you have what we call a polynomial equation, it's always going to have a domain of negative infinity to positive infinity, as long as nothing crazy's been added in there like dividing by an x, but then it becomes a rational function. So any polynomial function is going to have a domain of negative infinity to positive infinity. And 3.1 also gave you a list of toolkit functions that you'll need to know. So both of these functions were included in that toolkit in 3.1. Okay, given a function written in an equation form that includes a fraction, so this would be considered a rational function, find the domain. Okay, so identify the input values, identify any restrictions. In this case, we have the potential of plugging in a value and creating 0 in the denominator. So whenever you're trying to see, oh, am I going to hit a brick wall and either have 0 in the denominator, or am I going to have a negative value under an even root, which would give me an imaginary value output, you want to set up the situation that you do not want occurring. In other words, if I look at this function, which is f of x equals 1 plus 4x over 2x minus 1, what I want to avoid is plugging in some value for x that's going to make my denominator equal 0, because division by 0 is undefined, which therefore means that your entire function at that point is undefined. It doesn't exist at that point or at that x value. So what I want to do is set up the situation that I don't want to happen. In other words, I do not want, so do not want 2x minus 1 to equal 0, because if 2x minus 1 equals 0, then I'm dividing by 0. And I'm going to solve this equation to see when that's going to happen, because whenever that happens, I've got to exclude that from my domain. So to solve this is a simple linear equation. I add 1 to both sides, and now I have 2x equals 1, and then I'm going to divide both sides by 2, and I get x is 1/2. What this says is, if I plug 1/2 into the function, it will cause it to be undefined at that x value. And not exist on the graph. And I'll show you a picture of this. So that is the only value out of all of the real numbers that I cannot plug into this function. So before I show you the picture so that you believe me, I'll just say, okay, when we state domain, we state what we can have, not what we can't. We exclude those. So if I look at a number line, here's 0, here's 1, here's -1, out here is negative infinity, and out here is positive infinity. About right here is 1/2. Welcome, Kelsey. So I can plug in any value my little heart desires except for the value positive 1/2, because that's going to cause it to be undefined. So here's a picture of my domain. Now to write it out in interval notation, my domain, I always start with my lesser number. So I actually have 2 intervals for this domain. I start with negative infinity. Notice that's a parenthesis because I don't ever include infinity. I go up to, but do not include 1/2. So I'm going to write another parenthesis there because I don't want to include 1/2, but I can include anything between there. And then I write a U for union, or this is another interval because notice I've got now from 1/2 up through positive infinity. So this one starts at 1/2 and goes up through positive infinity, and they're both non-inclusive. So that is the domain for that function. Let me write that function down so I don't forget it, and we'll go and grab a picture of what that looks like so you can see what it means for a function to be undefined at a particular value. So I'm going to share my desktop again. And this time, my function is, let's see, 1 plus 4x divided by 2x minus 1. Okay. So, notice that we have 2 pieces of our function here. And if I can hit it on the money, if I can scroll out to 1/2, let me actually zoom in. I think that'll make it easier for me to get to, yeah, now I can really hit 1/2 here with an x value of 1/2. Notice if I scroll along the function, let's say I just click here, it's going to show you, okay, when I plugged in -1 into that function, I got out +1. And here, when I plugged in +2, I got out +3. But look what happens when I click on, let's see if I can get to an x value. Okay, so watch my x values. That's the first, let me actually zoom out some. That's the first value that's showing in the little point, the coordinate points there. So if I try to move up to 1/2, notice I'm not quite there yet. I'm getting closer and closer to 1/2, but I can't actually get to 1/2 because there is no function existing at 1/2. This is what we call an asymptote. We'll talk about these much later. And if I come to this side and try to get to 1/2, I can get close to it. So I'm really close. 0.5 is 1/2, and I'm at 0.568. But I'm just going to get closer and closer, but it'll never let me actually get to 0.5. So this is why we have those two intervals. You can either be on the left side or you can be on the right side of 1/2, basically, but you can't be exactly 1/2 because when you plug 1/2 in, it causes 0 in the denominator, which is undefined. And I'll show you that algebraically as well. What happens when I plug in 1/2 into that function. We're going to come back to the whiteboard. Okay, so when I plug in 1/2 into that function, watch what happens. Let me get a different color so it doesn't blend together here. If I do f of 1/2, that's 1 plus 4 times 1/2 divided by 2 times 1/2 minus 1. Well, my numerator, there's no problem. It doesn't matter if I have 0 in my numerator or not. So 1 plus, okay, 4 times 1/2, so 1/2 of 4 is 2. 2 times 1/2, 1/2 of 2 is 1, and then I have minus 1. So I get 3 over 0. There's the problem. I can't have 0 in my denominator because division by 0 is undefined. So I cannot include 1/2 in my domain. Give me a green check if that now makes sense to you, why you have to exclude certain numbers. We have two reasons that we have to watch out for. We have to watch out for 0 showing up in the denominator, and we have to watch out for a negative value showing up underneath the square root. Okay, great. I got 2 green checks on that. Okay, so given a function written in equation form, including an even root, so here's the other type of thing we have to watch out for. We have to watch out for negative numbers showing up under the radical. In other words, they show up in the radicand because the square root of a negative number is an imaginary number, and those don't even graph in the real plane. So we exclude those values. So we want to do the same process that we did with the last one and set up what we don't want happening to see when it's going to occur. And since we're taking an even root, we're taking a square root here, we don't want 5 plus 2x to be negative. In other words, we don't want that being less than 0 because that means it's going to be negative. So when I solve this inequality, that's going to show me all of the values for which this is going to occur. So to solve, I subtract 5 from both sides, and I get 2x is less than negative 5, divide by 2. So this is going to happen when x is less than negative 5/2, which is the same thing as x being less than negative 2 1/2. So if I look at a number line, I'm going to end up with a negative under the square root when x is strictly less than negative 2 1/2. So here's 0, here's negative 1, here's negative 2, and here's negative 3. This is negative infinity out here. This is positive infinity out there. About right here is negative 2 1/2. If X is strictly less than, then I'm going to have an imaginary number. If it is equal to or greater than, I'm safe. So my domain consists of everything that is exactly equal to, so I'm coloring in the endpoint there to say you can be exactly -2.5. You just can't be less than that. And it can be anything greater. So this is my domain. This is a picture of my domain. The way I would write this domain in interval notation, I can be, so I'm going to use a bracket because I want to include -2.5. I can go from -2.5, that's the same thing as -2.5, all the way up through positive infinity, and you never include infinity because that goes against the very idea of what infinity is. Now let's go take a look at this graph so you can see how, graphically speaking, this entire graph is not going to exist when it's less than 2.5 on the x values. So that is the square root of 5 plus 2x. Go here. Square root of 5 plus 2x. Okay, so square root 5 plus 2x. Okay, so I'm actually going to zoom in so you can see that that value, where that is stopping, is right at 2.5. Let me come out a little bit. Okay, so we have -1, -2, -3. Look, it stops right at -2.5. And when you plug in the value -2.5, you get 0 out as your output value. So I can't plug in anything less than that in the domain because it doesn't exist there. Green check if this is all starting to come together for you with domain and range. So we've looked at an example of both situations that we have to watch out for. And that's 0 showing up in the denominator of a fraction or a rational expression, and a negative value showing up beneath a root. So I see you're typing, Cyprian. I'm going to keep on going while you're typing because we're already going to be over time since we started late. Okay, so let me show you what happens algebraically speaking when you plug in exactly to -2.5. So when I plug in exactly -2.5, we already know from our graph we're going to get 0 out. That is legal. 0 is a real number. So 5 plus 2 times -2.5, that's -5. So this is the square root of 5 plus -5 is -5, which is the square root of 0, which is just 0. Now watch what happens if I plug in -3. How do you determine the less than sign? If anything is less than 0, sorry, hang on just one moment. It's my laptop picking up my phone, I apologize. The way I determined the less than sign, right, let me highlight it for everybody on the video right here, is because remember you set, God bless, hang on. You set up the situation that you don't want happening. Set up what you don't want happening. So I'm putting a frowny face for the lack of space here. So I don't want that expression beneath the root symbol to be negative. If it's less than 0, it's going to be negative. That's how I determine that, Cyprian. Does that make sense now? Okay, great. All right, so watch what happens, and I'm going to do this in red because it's going to create an imaginary number. If I plug in -3, which is less than, -3 is right here. It lies outside of our domain. So that is the square root of 5 plus 2 times -3, which is the square root of 5 minus 6, which is the square root of -1. The square root of -1 is I. That's an imaginary number. Because there's no real number that you can multiply by itself and get -1. So it's an imaginary number. So every value that you plug into this function that is strictly less than -2.5 is going to result in an imaginary number. And we don't want to include that in our domain because our domain is asking what real numbers can we plug in and get real number values in our output or in our range. So now we've seen an example of each. We've seen what happens when you could potentially have 0 in the denominator, and we've seen what happens when you could potentially have a negative value that you're taking an even root of. So other notations that can be used for for domain and range, we don't generally use these other notations, but they're out there. The most widely accepted way to write your domain and your range, unless it's not possible, is with interval notation. So we can have words. Okay, so if we look at this particular example, obviously the domain, and let me just highlight this in red so you can see it a little bit better because the blue on black doesn't show up very well. Okay, so we have this potential for our domain, then we skip that little gap, and we go all the way up to 3 non-inclusive. So in words, I can plug anything in from -infinity up to, and that's the and sign, including -2. Or I can jump to that other interval and that's anything from and including -1 up to but not including +3. Now, obviously, if we always had to write these words out, we would be spending a lot of time with something that we can symbolize quite easily with either set builder notation or interval notation. So writing this out in words is great for understanding it, but not so convenient when you're actually wanting to discuss this domain. So in set builder notation, we can see here some examples of set builder notation. We're talking about the set, so we use a brace when we're talking about sets. The set of all x's, I'm assuming that the input variable is x here. The set of all x's such that, this straight line symbolizes such that. Let's see, negative infinity is less than the values I want to talk about, and the values I want to talk about are less than or equal to -2, or -1 is less than or equal to the values I want to talk about, which are strictly less than 3. That's set builder notation. Still a little bit cumbersome and wordy. So I prefer interval notation. It's succinct, and as long as you know your symbols, it gets right to the point. So in interval notation, we would write this as this domain that we're looking at here starts at negative infinity and goes up to and includes -2, or it goes from and includes -1 up to positive 3 non-inclusive. So my suggestion is, unless you're asked to do otherwise in your homework or something, I would just always default to interval notation. Cyprian, I see you're typing something here. Okay. No, is that a no, you don't understand, or okay, an error? All right. Okay, so identifying domain and range from a graph. So another way we can identify domain and range is looking at a picture of a function, which we call a graph. Because domain refers to, and let me get a different colored pen to highlight this information for you because it's important. I would underline it or highlight it on your own set of notes. Domain refers to the set of all possible input values. So it consists of the input values which correspond to the x-axis. The range is the set of all possible output values, and that's going to correspond to the y-axis. And then it says, keep in mind, if it continues beyond the portion of the graph that you can see, then it's moving into infinity one way or the other, either negative or positive infinity. So like our function has this arrow. This means it's actually continuing both in our domain and our range. So if I continue to dot this out here, it's going more and more right, but it's also going more and more down. So I'm continuing to positive infinity in my domain and negative infinity in my range. So let's take a look and actually list this domain and this range for this function. Okay, so the domain, and I'm going to use the same colors that they have in the example here. My domain is basically, when you're talking about a graph, it's the span of your x values. So you always look at this from left to right, or so it's always, your domain is looked at from left to right. Range is different. We'll talk about that in just a moment. So this domain begins at -5. So my x values begin at -5, inclusive, because it's a closed dot there. And they're going to span all the way through positive infinity because this function keeps moving right, even though you can't see it. because it has an arrow on the end of it. So my domain for this particular function starts at and includes, so I'm using a bracket since I'm including it, -5, and goes through positive infinity. I use a parenthesis because I never include infinity. Let me stop there and ask, was that clear for you on domain from a graph? Kelsey says yes. Cyprian says yes. Very good. Now, range is a little trickier because you've got to flip your thinking entirely. Now, let me see if I can match that color pretty well. About right here. Okay. So now we're going to talk about the range. The range is the span of y values. So it's the up and downness of the function. And you read it from down to up. So if you notice, left to right and down to up go from negative to positive. So basically, instead of saying that this function's going down into negative infinity, it's actually coming up from negative infinity. Up, 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 all the way up to 5. So we're coming up from negative infinity, and it's going to keep going, up, 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 until I hit a y value of 5. So the range for this particular function comes up from negative infinity. Remember, you never include infinity, so I used a parenthesis. And it goes up to and includes a y value of 5. The reason it's inclusive is because there's a closed dot on the end of that function, not an open circle. How is that for range? Kelsey says it was good, and Cyprian says it was good. Awesome. And I'm sorry I've got y'all over the hour, but we didn't get started until about 20 minutes in. We were having some technical issues. So the video shouldn't be too much past an hour. Should be right at an hour. Okay, so let's find the domain and the range for each of these functions. The first one is just a generic function that you've been given there. It looks like it could possibly be a cubic, just from what I know of cubic functions. I will point out there's an open circle on this end and a closed circle on that end. And then we have another example, and I'll just go ahead and say these are closed circles. And this is a real world data type graph here. So let's look at the first example, and I'll stick with the colors that I used on the last page. So for domain, we want to look at the left and rightness of this graph. What I usually do is give myself barriers. I just come in and give dotted lines that frame my function from left to right. And if I've got an arrow on the end, I don't put a barrier because it doesn't end. And that tells me I need to move into infinity. But these have barriers. This particular one has barriers on both ends. So does this next one. I've got a barrier here and a barrier here because it actually ends. Okay. Since I'm talking about the left and rightness, I start at my lesser value, which is -3 non-inclusive, and this function's left and rightness expands all the way up to +1. So the domain for this function is -3. Notice I used a parenthesis because it's not included. That's an open circle. Up to +1, and it is inclusive because it's a closed circle there on that end. Now for range, we flip our thinking to up and downness. So I'm just going to put a barrier where I can. And all right. So since I have output values at the bottom here, that's a closed dot. I'm going to include -4, and this goes all the way up through and including, because of the top of the hump here, 0. Even though I have an open circle here, I have a closed circle at the top of that hump right there, which we'll find out in a little while in the next lesson, I think is called a relative maximum. So since that's a closed dot at the top of that hump, I'm going to include 0 in my range. So my range comes up from and includes -4 and goes up through and includes 0. How is that for you? Okay, Kelsey says it was good. Cyprian, what say you? Cyprian's good too. Very well. All right. So I'm going to go ahead and give my range barriers over here while I've got this color. Okay, so domain and range of this real world function here. Domain. It looks like I move continuously from and including the year 1950 all the way up to 2000 inclusive, because I've got closed dots on both ends. And my range, my output, comes up from, it looks like about 45 from what I can see here, and goes up to 90. Any questions about either of these on the screen here? Okay, it looks like, okay, I see your, okay, good deal, Cyprian. Thank you. All right, thank you, Kelsey. All right. Okay, so given the formula for a function, determine the domain and range, you want to exclude from the domain any input values that result in division by 0. You also want to exclude from the domain any input values that have non-real or undefined number outputs. That's that square root or that even root of a negative number. Use valid input values only to describe your domain and your range. And I'll be honest with you, it's easiest to get it from a graph. It's kind of tough to think about the equations just as equations, so that's why I gave you the prompt to go check the graph out. And that Desmos.com, that's what I've been using to show you these graphs this morning. It's a free online graphing calculator, and it's really good. So that's the first thing I'm going to do for each of these is go and grab the picture. So the first one's 2x cubed minus x. Now, we know from earlier in the lesson, this is a cubic function. And you should remember that, from what I told you earlier, that the domain of any cubic function is negative infinity to positive infinity. And I'll also tell you that the range of any cubic function is also negative infinity to positive infinity. But let's take a look at the actual picture of it. Okay, so our function that we wanted to look at is 2x cubed minus x. Okay. So I'm just going to zoom out so that you can see this thing keeps going and going. Makes an S across the, or we call that an S, across the x-axis there. Let me grab a picture and we'll go and draw on it. On our whiteboard. Okay. Make it a little smaller. Spread it out a little bit, even though it distorts what it really looks like. Makes it easier when we're trying to identify what's going on. Okay, so first thing I'll point out is that the tail ends of this function keep on going in that manner. So on the rightmost side, it's continuing to move out, 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 out to the right and up, 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 up. It's continuous. So I put an arrowhead on the, I'll put the arrowhead right here. It's continuous. Same thing in this direction. It's continuous. So with this direction, whoa, that was really bad. It keeps moving left, 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 and down, 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 down. So if I try to put boundaries on my domain, I can't put boundaries where it actually stops because I've got arrows on both ends. So my domain is from negative infinity to positive infinity. Flip our thinking, I also, for my range, have arrows on both ends. So I move from negative infinity to positive infinity. Y'all good with that one? Green check or red X? Okay, green check from Kelsey. Green check from Cyprian. Awesome. Let's take a look at this next one. 2 over x plus 1. Okay. So 2 divided by x plus 1. All right. Let me get a screenshot of this. And we'll come back. Paste it on here. Okay. All right. So let me point out that you have a variable in your denominator of your function. This is going to cause potential to have 0 show up in your denominator. So it's this situation right here. You have to be aware of this when there is a variable that you can plug into in the denominator. I'm just going to put denom or denominator. So what I don't want happening, I don't want x plus 1 to equal 0. That's going to happen when x is negative 1. And now, if you look down at our picture, right at negative 1, I'm just going to put a dotted line, you can see this is actually called an asymptote. you can see that my function approaches that value of -1, but it never actually gets there. That's because the function does not exist at -1. So I have to exclude that from my domain. Let me go back to my color coding. My domain here. It comes from -infinity all the way up to, but does not include, I'm going to put a big old open circle there, -1. But then it picks right back up and moves through positive infinity. So my domain goes from -infinity to -1 non-inclusive, or I can be in the interval from -1 through positive infinity. My range, okay, so I also do not exist at a y value of 0. You can see it runs, it's going to run close to the x-axis, but it's never actually going to get there. So in my y values, I come all the way up from -infinity, but when I hit 0, I don't exist, and then I move all the way through positive infinity. So my range comes from -infinity up to, but not including 0, or from 0 through positive infinity, non-inclusive. And this last one, negative square root of 2 minus x. Okay, so negative square root negative square root, square root. Oh, why is it not letting me do that? Let me take the negative off and see if I can put it back in. Okay, square root of 2 minus x, and let me make this negative. There we go. Okay, so let me grab a picture of it. And we'll come back to the whiteboard. And paste it here. Make it smaller. Fit it. Okay. Okay. So, algebraically speaking, we have an even root. And whenever we have an even root with a variable underneath, we could have the potential for imaginary numbers. So this is the potential when a variable is under an even root. So what we don't want happening, we don't want 2 minus x to be less than 0, because that means it's going to be negative. So I subtract 2 from both sides, and that gives me negative x less than negative 2. Divide both sides by negative 1. Now with an inequality, whenever you divide through or multiply through by a negative number, you got to flip the sign. So this is x is greater than 2. So in other words, when x is greater than 2, this thing's not going to exist. So when this happens, this is where it does not exist on our real number graph. All right, so let's take a look at the picture of it. So domain, I can definitely put a barrier over here. And this is a closed circle on the end here. So I can't put a barrier on the other side because this is technically an arrow. So I come all the way up from negative infinity up to and include positive 2. But I can't go past it. You can see that the graph doesn't exist past that x value of positive 2. So my domain comes from negative infinity and goes up to positive 2 inclusive. My range, you can see it's never going to go above the x-axis there. And it's going down, 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 down. So it's going to come up from negative infinity, and it's going to stop and not exist past 0 in the y values. So my range comes up from negative infinity, and it goes to 0 inclusive. Y'all good with domain and range here? I've got 2 more slides left. I appreciate y'all sticking with me. Okay, so we also have these things called piecewise function. And the piecewise function is when you have a function that uses different formulas for different pieces of its domain. So it's literally, that's why it's called piecewise, because it's a function that's going to end up showing up in pieces. So you always, with a piecewise function, have to have what we call domain restrictions given. In other words, if I'm following that first expression for the function, I have to be in a particular domain. If I'm following the second, I'm in a different domain, and so on. So if you look at this example up here, let me not use that color because that's the color I've been using for my range. So look at the example up there. You can see that in your domain from negative infinity up to, but not including 6, you're going to be using the piece of the function that is x squared. So if I were going to write the function for this piecewise here, it would be f of x is equal to, well, I'm going to have 3 pieces. You can see I've got 3 different functions happening there. My first piece would be x squared, and this is if my domain, so if x lives in the interval from negative infinity up to, but, oh, I'm sorry, that should not have been a bracket. That should be a parenthesis because it's infinity. When my domain is from negative infinity up to, but not including 2, I'm going to be graphing x squared. I'm going to be graphing f of x is equal to 6 if x is exactly equal to 2. And I'm going to be graphing f of x is equal to 10 minus x if x lives in the interval from 2 non-inclusive up through positive infinity. So let me stop here and ask, does that make sense? What a piecewise function is, how you determine what expression you're going to be using to graph that piece of the function. So you've got different domain rules that apply for each expression. Cyprian, is that okay for you so far? We've got 1 slide left. Okay, very good. Okay, so we're going to write a piecewise function, and then we're going to graph a piecewise function by hand down there. Okay, so a museum charges $5 per person for a guided tour with a group of 1 to 9 people. Or they charge $50 fee, just a fixed flat $50 fee for 10 or more people. Write a function relating to the number of people in and the cost, C. So, C of n, that's like f of x, C of n is equal to, I've got 2 pieces, so I need to mark it with a big brace showing that this is a piecewise function. $5 per person. So that's 5x. $5, or I'm sorry, 5n. That says $5 per person. That only happens if 1 is less than or equal to x is less than or equal to 9, or I could have written it if x lies in the interval of 1 inclusive up to 9. I could write it either way, and you'll see it written both ways. You can see here this is written in inequality notation, but you could just as easily use interval notation. So, and actually I take that back because you can't have partial people. That is a broken interval, so you cannot write that as interval notation. That one has to be written, and really it's incorrect since you're talking about people to even use that inequality notation. Really it should be if x is equal to 1, 2, 3, 4, 5, 6, 7, 8, or 9. And there's a reason we're not graphing this, because this graph would get crazy. It'd just have dots at each of those because you can't have half of a person, so it's not continuous. But this is just the idea of how to set up a piecewise function. Okay, so the next piece of it says, well, your cost is going to equal exactly $50 if x is greater than 10. Greater than or equal to 10. So 10 or more, flat fee of $50. That's how you'd write that piecewise function. Okay, let's finish this lesson off by graphing this piecewise function down here at the bottom. So, what I always do when I am hand graphing a piecewise function is I give myself what I call domain barriers. So this first piece of the domain is going to go from -infinity all the way up to -1. So that's my first barrier. I have a barrier where I'm going to switch my functions at -1. Whoops. And I also have a barrier at 4. You can see in my next domain restriction here, I go all the way up to 4. So in between those 2 yellow barriers is where that middle function is going to live. And then everything after that is going to be my last function. So this is just my own method of doing this by drawing those barriers in. But you get those barriers from looking at, okay, what part of the domain am I going to be working with this particular function with? Okay, so I'll do each of these pieces in a different color. We'll start with f of x is equal to x cubed. Notice I can, when I create an f of x table to create points to put on the graph, I don't want to choose anything that is exactly equal to or greater, or greater than -1. So I'm going to choose a few more values. I'll choose -4, -3, and -2. So when I cube -4, -4 times -4 times -4 is -64. It's off the graph. -3 times -3 times -3 is -27. And -2 times -2 times -2 is -8. That's the only one that actually shows up on the graph. So -2, -8 lives about right here. -3, -27 lives way down here. It's already off the graph. So this piece of the function comes up and when it reaches -1, and actually that's a bad rendition of that. Let me go ahead and see what happens exactly at -1, because that's our barrier. -1 times -1 times -1 is -1. So when I come up with this piece, when I reach -1, at -1, it's going to be an open circle. So I come all the way up, and for this piece, when I reach -1, -1, that's an open circle because I cannot exist there. Okay, the next one. F of x is -2. This says no matter what x is at this point, f of x is -2. So if I create an f of x table, got -1, 0, 1, 2, all the way up to 4. And it's non-inclusive at those. So I have an open circle here. We'll go ahead and do 3 and 4. And I have an open circle at 4 because it's non-inclusive. This says, because this is a constant function, and we talked about the constant function in lecture 3.1, says no matter what you plug in for x, y is always going to be -2. So I have the point -1, -2, and it's an open circle because I can't exactly equal that because it says strictly less than, not less than or equal to in my domain restriction. And that's going to go all the way up to +4, but it's also going to be an open circle there because it doesn't say exactly equal to. So between there, this part of the graph is just a horizontal line. And then my third piece is f of x equals the square root of x. And I start at 4. But I'm not going to include it. It's going to be an open circle at 4. And we'll do 4 and 9. Those are the two that are on our graph, and they're perfect squares. So when I take the square root, I get an integer. Square root of 4 is 2. Square root of 9 is 3. So at 4, 2, I have an open circle. And then I also have the point 9, 3. So this zooms off like this into positive infinity. That's how you graph a piecewise function. You literally graph it in chunks like that. That's all I have for y'all today. Do y'all have any questions about anything on the screen or any of the old slides that we've already passed? Okay, Kelsey says she's good. Cyprian, how are you doing, man? All right. Well, thank you both so much for hanging in with me after our allotted time for this lecture. I appreciate you showing up. I have another lecture this afternoon at 3 o'clock. If you can make it, great. If not, have a wonderful weekend. Thank y'all. You're so very welcome. I'm glad